Okay, I want to talk to you now about how you construct molecular orbitals for heteroatomic molecules. Now, there's some rules that I have in the PowerPoint, and you can go through them. They're not too bad. They kind of like give you a summary of how to go about looking at this type of orbitals. Now, generally speaking, though, what I'll point out is that if you have a molecular orbital that's considered to be bonding, you must have more bonding orbitals than you do have anti-bonding orbitals. If you have a bonding orbital that is overall anti-bonding, you're going to have more anti-bonding than bonding. And if you have equal amounts of both, then technically this is non-bonding. Alright, but I want to show you just a few examples. I'm going to focus on HF and CO. Now this is the heavy-duty way of treating the molecular orbitals. I'm simply going to be more mellow when it comes down to them. I'll ask you to either correlate the molecular orbital to that of lithium through nitrogen or oxygen through neon. And the idea is that if your molecule contains any of the oxygen or fluorine atoms, automatically you go with the molecular orbital for the oxygen. If it does contain just elements lithium through neon or any of the bigger partners on groups 1 through 5, then you stick with the lithium nitrogen diagram. But I'm going to show you how to do this the proper way. Alright, so if we look at hydrogen fluoride, the difference in energies of the 2s and the 2p's orbitals of the F element are rather large, are super large in fact, so they don't really interact with each other. But notice that the energy of the hydrogen atom is actually very close to that of the 2p orbital of fluorine. The one for the 2s orbital of fluorine is actually very low compared to hydrogen, so the interaction is going to be rather minimal. And the picture looks kind of something like this. Hydrogen is a little bit larger than fluorine in terms of its energy, but the s orbital of fluorine is very low in energy. So the interaction is going to happen mostly what's happening right here. S orbital with p orbital. So the s orbital is mostly going to remain untouched and it's going to remain roughly the same vicinity. 2 out of the 3 p orbitals don't have the right symmetry to interact with this orbital. Only the p orbital that is head on gets to interact with this s orbital. So that's the only one that creates a sigma bond and a sigma star bond, right? So in phase and out of phase. Alright, and so also because we're a little bit off in terms of the scale, right? We're not exactly the same point. I'm kind of, equilibrating a little bit, how much I go down for the sigma, how much I go up for the sigma, right? And I account for the fact that there's 0.4 Rydbergs of difference here, so I'm allocating for the fact that this should be roughly 0.5 Rydbergs altogether. I should go up in value for sigma star and down in value for sigma. Alright, but we have a relatively okay molecular orbital diagram. We have 1 electron for hydrogen and we have 7 for fluorine, so 8 altogether. So we start plugging in from the bottom. We have 2 electrons, followed by another 2, followed by another 2, and ending with another 2. So we have 8 electrons. And one thing that's worthy about this is that pretty much all the electron interactions that are happening are bonding interactions or non-bonding. Notice that the p orbitals here that didn't get to interact with anything are basically the same energy. We call those non-bonding orbitals. And that basically tells you that yes, a good chunk of the electrons of fluorine are going to be basically lone pair of electrons. So it's kind of cool to see that. The other thing too is that yeah, so we see a little bit of the anti-bonding interaction right here, which is the sigma star. This actually tells you, roughly how the acidic, nature of HF is going to take place. Is via these orbitals. All right, let's finish this up by talking about carbon monoxide. It's a little bit harder of an example because you have 2s and 2p sets for each of the 2 atoms, but they are off scale from each other. Oxygen has a larger gap in energy between its orbitals than carbon. But the 2s orbital of carbon is kind of in between the 2p and the 2s, so there's going to be some interaction among them all. Alright, now specifically, s orbital of carbon here is going to go down a little bit in energy compared to the 2s of oxygen, and it's going to go up a little bit compared to the 2s of carbon, giving you sigma and sigma star. At the same time, your 2p sets are going to give you sigma, pi, pi star, and sigma. But because the 2s of the carbon and the 2p of the oxygen are kind of close in energy, about 0.3 Rydbergs of energy, these two orbitals, the sigma star and sigma, will interact with one another, and they will give you a lower energy orbital and a higher energy orbital, kind of raising that sigma orbital once again higher up in value. And what you end up with is the following molecular orbital diagram. Now, carbon has 4 electrons as valence electrons, oxygen has 6, so we're talking about 10 electrons altogether in carbon monoxide. So we start plugging in the values for the given orbitals of carbon monoxide. We have 2 electrons down here, followed by another 2, that's 4, followed by 4 more, that's 8, and another 2 to give you a total of 10. And if we look at the 4-electron spectroscopy of carbon monoxide, we actually get to see that, yes, the last orbital where the last electrons, the number 9 and 10, are located are in an orbital that barely has any splitting on the peak. And what this is telling you, at least the 4-electron spectrometer is telling you, is that this orbital has roughly non-bonding interactions. The ones that are either bonding or anti-bonding, they have a lot of peaks, like you see right here. Like your pi and your sigma star, they have a lot of peaks because they are actually affecting the size of the bonds as you start messing with the electrons present in them. Alright, so that's actually pretty good. And then if you do the actual calculation, you'll find out that you end up with a triple bond in between carbon and oxygen. Now the last thing that I want to point out, because it's actually kind of cool, is that the last set of electrons, the sigma and the pi star, is what we call the frontier orbitals, and to some degree they are involved in the chemistry of the various molecules. Now, carbon monoxide is a very notorious gas. It's basically a poison that you don't get to smell. If you ever have a furnace that's kind of like partially burning wood, you're actually getting some amount of carbon monoxide, and this is actually pretty dangerous because you really don't smell it. You don't have sensory nerves that actually smell CO. But the thing about it is that it interacts with metals very well, because the orbital that's empty, the pi star orbital, which has the following setup, has these head-on p orbitals with the pi star bond. But those head-on p orbitals are perfectly allocated to interact with d orbitals, forming yet another pi bond. And on top of that, the sigma bond of the last set of electrons are basically allocated to work in the sense that they can actually donate electrons into a metal and create a sigma bond, and in doing so they basically lock in with transition metals. And one specific example is the heme unit of hemoglobin and myoglobin, which is one of the reasons why you actually can get carbon monoxide poisoning, because technically speaking carbon monoxide binds so well to these things that it prevents the proteins from actually acquiring oxygen and transporting it from the lungs to the muscles and cells, which eventually kind of kills you. So that's kind of the reason why this happens, but there is a molecular orbital description of why it happens, which I think is rather elegant. Alright, so with all of this in mind, we have quite a number of tools to describe bonding, and I know that there's quite a bit of material, but hopefully you start seeing some of the nice intricacies about bonding. If you do have questions, feel free to join me during office hours. You have to see this material a few times before it finally clicks in. This is as chemistry as it's gonna get in this class, and as abstract, if you will, as it's gonna get. But hopefully you see the joys and the little intricacies behind it. Alright, well, with that being said, I'll leave you right here. So see you soon.